Okay, let's talk about statistics on the SAT. When I say statistics, I mean stuff like mean, median, mode, range, standard deviation. And honestly, this is something you really need to understand for the SAT, because though it may not appear all of the times where it does appear, there is no replacement for it. If you don't know how to do this stuff, you're just going to be absolutely cooked, and there's not really any way around it, especially if you get a more complex mean, median, mode problem. And I have seen SATs where maybe even the hardest or one of the hardest questions on the test involved mean and median. It does actually happen. If you want to know why you should trust me, I scored a 1550 on the SAT. I've helped hundreds of students improve their SAT scores before, and I'm trying to make the channel you're watching right now the best SAT channel on YouTube. Okay, statistics, just to get this out of the way, is anything that involves a group of numbers. So we all know what numbers are. Hopefully you do if you're watching the channel, if you've done at least some kind of math in your life. You know what a number is: 1, 2, 3. But what if you have a group of multiple numbers? Like what if we put all of these together? So you have 1, 2, and 3 all together in one solid group. That is something we could do statistics on. And another way you can think about it is, let's say you have 5 different friends. And let's say you're trying to tally up how much money every single person has. I guess I always just think about money for whatever reason. So this person, let's say they only have $20 in their bank account. Meanwhile, this person is a bit more wealthy. He has $100 in his bank account. This person, pretty solid, has $1,000 in their bank account. This person is actually having a pretty solid income. They have $50,000, let's say 50K. But then you have this person who invested in crypto early, and he literally has a net worth of $1 billion. Yeah, this guy, he is not really like the others. He's the black sheep of the group, or I guess, the good version of that, whatever. So he is a very rich friend. What if you're trying to calculate what is the average amount of money held by one person in the friend group? Statistics is basically all about answering that exact question, or other questions like how far spread apart are the different incomes of this friend group, stuff like that. So let me go over some of the major things you need to know with statistics. The first thing is mean. You probably have heard about this before. If you haven't, I really do not know what you've been doing. This is like 5th grade math level stuff. But basically, if you want to find what basically is the center, like the major point of a set of data, you can add up all the different data points and then divide by the amount that is listed. So if you have this group of numbers here, 5, 6, 7, 10, 17, you can add them together, divide by 5, and that gives you 9 for the mean. But this is a good time where I should probably mention Desmos, because a lot of this stuff that I'm about to go over and this itself can be solved literally just using Desmos on the test. It actually simplifies it a crazy amount. All right, so here's how it works. If you type any kind of letter besides X, Y, or E, don't use those. So if I said like A, and I say equal to square bracket, I can now give a list of different data points to put this in. So I could say for this example here, we have the 20 person, the 100, the 1,000, the 50,000, and then we finally have the 1 billion person. Now we have all these numbers saved in this one data point A. So I can actually do operations on A to find this different information. And one of the easiest ones I can do is just mean of A. We can see with this that the mean of these 5 different data points would be 200 million. So really important to know. So this is how you would solve any of this stuff with Desmos, and I'll give some more examples later on. Back to the mean discussion though, you may notice that what the heck? This is literally 200 million. Would it be fair to say that the average person in your friend group has a net worth of $200 million? Not really, because for 3 people, that's definitely not true. For one person, that's closer, but yeah, still nowhere near 200 million. And then we have one person who has, honestly, even a lot more than 200 million. So that's the big issue with means. You can see it with this example. It is heavily skewed if you have a very, very big number. And this makes sense because think about what's going on here. We're literally adding together every single thing listed here and dividing it by the total amount. You can see that 1 billion number is going to really make it so much higher than it would be otherwise. And so practically all of the weight is just going to the 1 billion because that's way bigger than any of these other numbers. So add them together, divide by 5, you're going to get a crazy big number like this. So that's where the other stuff is going to come in a second. But yeah, mean is still useful because you can just see in many cases what the average thing of a set of data would be. But for stuff where there's big outliers, it's almost never going to be used. For example, if you're trying to calculate the average wealth of an American, the mean is going to be so much bigger because you have the billionaires in our society, even trillionaires maybe, who are bringing up the total amount of money that people have. So other stuff is more typically used. Let's solve some problems. So you can see some very easy statistics problems, and then you can get some harder ones. Let's go over an easy one first to start off with. A student recorded a number of pages read each for 5 days for a group of people, I guess. Which is the mean number of pages read per day? For something like this, I can just go ahead and type in A and then give in the things so like 12, 15, 15, 18, 20, and I can just go ahead and say mean of A, which would give us 16. If you want to make this process even simpler than that though, I could even just literally drop this in for A, so mean of that, and we just get it immediately. So you don't have to make it as a variable if you don't want to. What if we make it a bit harder though? So this is one where you're gonna have to actually write some of your own equations, build your own equations type stuff. So the way to solve a problem like this is you have to actually make equations based off of each of these scenarios. So think about what's going on here. What mean is basically the sum of the data points divided by the total amount, I'll say n for amount, equal to the mean. That is what the mean literally is. And so what you may not think about though, is that we could just write this as an equation. So with this example here, it says dataset A has mean of 35. What that really is saying is that if you add together all the numbers for A, let's say that's this letter here, and divide by the total amount of things in A, let's say it's lowercase a for that, that would be equal to 35. Think about what's going on here. If it doesn't make sense, really try and understand this because we're going to go into some more detailed stuff with this in a second. So if you don't understand this, it's going to be really hard what we're about to go over. Okay. Dataset B has a mean of 80. So I'm just going to do the exact same thing. The sum would be that, and the amount would be this. So that would be equal to 80 for the mean of that. And then says you put them all together, and there are now 120 values in both A and B added up. And that has a mean of 50. So I'll write this one here in Desmo. So we can basically say A plus B, so add together both things, divided by 120, must be equal to 50. That is what is going on here. And the other ones, just to write those as well, would be equal, that. Then we have this one equal to 80. And we have these three different equations here. Can you tell what the problem now is? Well, if you've watched my videos before, you would know this very fundamental math rule, which is that you must have the same amount of equations as you have variables, or more equations than variables, in order to solve something in math. But if we look at this, we have 1, 2, 3, 4 different variables and only 3 equations. So there's a mismatch. There's too many variables and too little equations. So we need to find a way to either add an equation to get to 4 equations, or to remove a variable so we can get to only 3 variables. I'm going to choose the second option. Let's see if we can remove one of these things. One very easy thing we could do is just, instead of saying B, we can say 120 minus A. Now, just try to understand what's going on here. A plus B together must equal 120. So if we do 120 minus A, that by default would be equal to B. That's the amount that's in dataset B, because we're just taking 120 and removing a amount of the things in 120, whatever's left is whatever. Okay, so now we have only 3 different variables and 3 different equations. I'm just gonna go ahead and solve this using regression without a table. The reason why is because whenever you have at least 3 variables, it's recommended to use this method instead of solving it just with the regular equations. So I'm just gonna go ahead and do this. I have a video on this if you want to see more how to use regression without a table. Very good stuff, would highly recommend it. It's hard to understand otherwise. Okay, we can see for this, it is asking what are the amount of values in dataset A. Lowercase a would be equal to 80, so therefore 80 would be the right answer here. Pretty good stuff there. Okay, now let's go on to the next major thing, which would be, of course, median. What a median is basically just the center point in a set of data. This is what mean was supposed to be before all these big numbers ruined it. You literally just take all the numbers from lowest to highest and find what is the center point of that set of data. In this case, the center point would be 7. Back to my crypto billionaire example, you can see the median of this set of data would literally just be 1,000. So, okay, you could see, even though we kind of are just leaving out this 50,000 guy and the 1 billion guy, this is definitely a lot more fair as for the overall average net worth of the person in this friend group. So you can see it is literally just the center point. The point right in the middle would be 1,000. That's why the median is 1,000. If we had an even number of people, so for example, if we had another person in here that had like 1,500, then they just find the mean of the 2 middle points, and that is the new median. So in this case, it would be 1,250 because 1,000 plus 1,500 divided by 2 would be equal to 1,250. So a lot more fair, and you will actually also notice, back to my example about wealth in America, if you're looking at data on like the average wealth of someone in the United States, it's always going to give you the median number, not the mean, because they know the mean is just so skewed, it's so cooked, it's not really that good. Though actually you will discover if you look this up that the mean is not that crazy, but just it's noticeably bigger than the median. Okay. As for some examples, let's give an easy one again. Here's a score on the quiz for 7 different students. All I would have to do is just say median, because that's the function for this in Desmos. 72, 88, 91, 75, 74, 88 again, and then 90. Median of that would be 88, so therefore that's the answer. Harder example now, we have this set of numbers and x is one of them. It says the mean and the median are equal, which choice is not a possible value of x. So there are different ways you can approach a problem like this, but I would just say just go for the easiest way, which is just literally write something like this. So I could say a is equal to 3, 8, 8, 11, 14, and then x1. I have to put the 1 there because otherwise it's going to treat it as a variable. We need it as a constant because it's only one number. And then I can just go ahead and say, mean of A and then median of A and just change around this number to see where it actually matches up. So I know a little bit tedious having to actually write out the stuff, but it's just so easy that you're not likely to be making mistakes, so you might as well do this. Okay, go ahead and try out each of these numbers and see which one works. So 4, they would be the same. We're trying to find a place where it would not be the same, so that cannot be it. 10, okay, same thing, they're the same. 13, again, the same, so we know that D must be the right answer. Yes, they are different when you have it being 16. Okay, that was a good problem. Now let's go on to the one that's just actually very hard. So we have an ordered data set with 11 different integers. The mean of the 5 smallest is 18. The mean of the 5 largest is 32. The mean of the entire data set is equal to the median. What is the value of the median? Okay, let us actually think about what is even going on here in the first place. So we have 11 different numbers here. So a way you could think about this is an odd amount. So we could have a median value, because remember the median is always the middle point. And then we basically have 5 different points on this side, and then also 5 different points on this side. So 5 here, and then 1 right in the middle. And then it says the mean of the 5 smallest would be 18. So if we think about the mean of this, that's 18. And then the mean of the 5 largest would then be 32. Okay, so pretty good, pretty easy so far. And then it says the mean of the entire data set is equal to the median. So if we found the mean of the entire thing, this would actually be equal to m, because m is the median. That would also be equal to the mean according to this line down here. What is the value of the median? So similar stuff to that problem before. We can just write equations for each of this different stuff, and that should hopefully give us the right answer. So we can say, let's say s for the sum of the smallest amount, and then s divided by 5 must equal 18. Then we can say, I guess, L for the larger ones. So L divided by 5 is equal to 32. Just the same stuff we did before, sum divided by amount must equal mean. And then it says here that the mean of the entire thing, so we can say S plus L plus M for the median value, because we have that 11th one in there as well, divided by 11 must together equal M again, because M would be the same as the mean. Remember that. I'm just doing that because of this one line here. That would not normally be the case, that this thing would be equal to M. Okay. Good stuff there, and I'm just going to go ahead and use regression yet again on this problem, put these in. With this, we see that m, aka the median, would be 25, so therefore the answer would be 25 right here. Let's just go over a few quick things, the mode and then the range. Mode is the most common value in a data set. So for this here, the most common thing would be 6 because it appears 2 times. So that is what a mode would be. Thinking back to our crypto example, there would not really even be any mode in this data set because they each just appear one time. There would only be a mode if there was one that also appeared a second time. So for example, if this person lost some of their money in blackjack and now they also only have $20, then the mode of this would be $20 because that's the most common value. Otherwise, there's not really any mode. Or you could argue that there are multiple modes because every single thing could be an individual mode. It doesn't really matter. You also will not see this too often on the SAT, so not really that important to know. Second thing you don't really need to know that much is the range. This is a bit more common than the mode at least, but also not that common. What the range is just the biggest value in data set minus the smallest. So then in this case, it would be 17 minus 5, 12 would be the range. And yeah, that's all you have to do for that as well. A big thing as well to know is that you can't actually put these in Desmos. If you put mode, that is not like an actual thing. If you say range, also not an actual thing. So don't try putting those in Desmos. You just have to solve them yourself, but thankfully not too bad. Standard deviation. Okay, now let's go to some stuff that is a bit harder that you can use Desmos for, but not too bad. What standard deviation is the spread of a set of data. So thinking about this set of data would have a lower standard deviation than this one. Why would that be the case? Well, because in this one, they're all pretty close together. 5 is only 3 things away from 8. And 6 and 7 are pretty close, 6 and 5 are pretty close, 6 and 8 are pretty close, all that. 3 is the farthest distance of any 2 numbers in this data set. Meanwhile, we have this one, think about it, these are like really far apart. 10 is 80 away from 90, 80 different things away. 20 is 70 away from 90. 80 is 10 away from 90. So a lot more spread out. If you're trying to write out like all the numbers between 0 and 100, for this one, if we put a dot for every single thing, it would all be very scrunched together. Like it would be very close all together at this part of the line. Meanwhile, this one, it would be very far spaced apart. We'd have one like over here, one over here, one over here, one over here. So very far apart for the spread for the second one, whereas very close for the first one. That's why it has such a small standard deviation. You can put this in Desmos just by saying stdev. And keep in mind, it has nothing to do with how big the numbers are just overall. So if I said here something like 50, 51, 52, you may be thinking that should have a big standard deviation because they're all big numbers. But that's not the case. The standard deviation is literally just 1 because these are like very close together. 50 is very close to 52. Even if it's something absolutely crazy, like if we had like what is that, like 10,000 and then 10,001 and then 10,002, still it is literally just 1. So it has nothing to do with how big the numbers are overall. It just matters how far apart they are from each other. So if we had this one being like 1, now we have a huge standard deviation because 1 is very far apart from 10,001 and 10,002. And yes, for those of you thinking about it, this would also have a very big role in our crypto billionaire example. Because if we have 20, 1,000, 50,000, and then 1 billion, like, whoa, we have like literally 447 million for the standard deviation of this. They are very far apart, very high amount of spread for this. They are not close in any way. Now, thankfully, you do not need to actually be able to calculate the standard deviation. If you want to know what the standard deviation is, the basic definition is that it's the mean of the amount that the different data points are away from the mean of the data set. If that made no sense, no worries. Again, you do not need to know how to calculate this. You can just always use Desmos every single time. And many problems, I'm not even going to ask you anything about it, so you probably won't even need to do this. You just need to know what it basically means. Like, it means spread, essentially. Real quick before we move on, I just want to mention that mean, median, and mode, these are known as measures of the center of a set of data. So that should make sense. They're basically talking about, what the major point of the data is. That's the key thing going on here. Whereas range and standard deviation are instead talking about how spread apart they are. They're measures of spread instead. So not really that important that you know, more just like a naming thing, but just so you know that, I guess. Quick, harder example. A farmer recorded the masses of these pumpkins entered in a contest. The mean mass was 58 pounds and the least mass was 41 pounds. Okay, so I think you're probably good enough at this point that I can actually just write this straight into Desmos rather than writing it down here first. So just to write that first equation, we could just say here, let's say S would be the sum and then N is the amount, and that mean would be equal to 58. Second one here, if the 41 pound pumpkin is replaced with 56, the mean of the new things becomes 59. So that would basically be saying minus 41 because we're removing 41 from the data set, adding 56 because we're adding that into the data set, and we divide that again by n because there's still only n amount. Whatever amount doesn't change because we took one away, but then we added one back in as well. So that now becomes equal to 59. Pretty good. But then it says if instead the greatest mass was replaced with a 47 pound pumpkin, the mean becomes 55. So we can take this exact same thing, but we do not actually know what the greatest mass is. We have not heard about that at all. We know about the least masses, but not the greatest one. So we can just say in this basically S minus G and then add 47 to it. So pretty good stuff there, and that would be equal to 55. Similar stuff as before, we have 3 different variables and also 3 different equations, so I can just go ahead and use regression without a table. Okay, some good stuff here. We have these different values for S, N, and G. It says, what is the range of the original set of masses? As a reminder, range is a measure of spread, so it's the biggest minus the smallest. So we could just take the biggest thing here, which would be equal to G, 92, and then minus the smallest, which it told us was 41. So minus 41 would be equal to 51. 51 is an answer choice, so I select that. Box and whiskers plots. This, like standard deviation, is not really that important. All that really matters is that it kind of looks like whiskers on a cat. I guess you could say, this is a whisker, that's a whisker. Whatever, I don't really care. Nobody really cares about that stuff. But you do just need to know how to basically evaluate this. When I say basically, I mean evaluate it in a basic way. So if you see something like this on the SAT, you need to know the minimum value is the thing over here, the maximum value is the thing over here, and the median value is the thing in the middle here. You should hopefully be seeing different numbers at the bottom here. So this might be like 0, this would be 1, 2, 3, 4, 5, 6, so this would be 6, and this would be like 12. So that is how you'd evaluate it. So for this data set, the minimum value would be 0, the maximum would be 12, and the median value would be 6. You do not need to know anything about these 25% numbers or the Q1s, so just forget about those, don't worry about it, it's all good. if you see something on the SAT like this, just know these basic information about it. Now onto data operations. So what if you went ahead and took all of these different people from before? So this guy, he lost some money in blackjack, but everyone else is the exact same. And then you went ahead and just gave them all a big government subsidy. Now this is not a political statement here. I'm just saying, what if you literally just gave them all some money? Like, let's say you gave them all like $1,000. Now every single person is going to be $1,000 richer. If we were to look at the data, it would be like 1,020, 1,020. Then we have now a person with 2,000. Then we have someone with 51,000, I guess. And then like we have like all this numbers. And then, so $1 billion and $1,000 for that last person over there. Okay, so this is the new data. How would the mean, median, mode, range, standard deviation change? How would that actually change for this? Well, if you were to go ahead and just add a data point like I just did here, or subtract a data point like I could theoretically do, I guess if like the economy is really bad, everybody loses their money, then all you change is the mean, median, and mode. All those values will definitely change. Same thing would be the case for the median. Obviously, that's going to change because the middle value is not the same anymore. It's now 2,000. And then if I were to calculate the mode, it would not be the same. I mean, there's not really any mode. I mean, yeah, the mode would just be 1,020 and rather than 20. So yeah, plus or minus is both going to change those three things, but not the range or standard deviation. If I want to prove this, if I were to go and change it back to what was before, and then we go ahead and calculate the standard deviation of this, it would be this 447 million number. Now let me go ahead and add the government subsidy back in. You can see it is literally still 447 million. No change was made literally at all. Standard deviation is the exact same as it was before. Same thing if I were to calculate the range. Think about it. The range is still going to be this huge, unbelievably big number minus a much, much smaller number. The only difference is now they're both $1,000 richer. However, you can probably see where I'm going with this. If we were to have multiplication or division in here, it would change literally everything because now all these numbers can be very vastly different, unbelievable. It's kind of like, I guess, if all these people invested their money and now they're all much richer, but that kind of stuff. Just trust me here. It's going to change every single thing if we were to do it, including range and standard deviation. And we can see this in a problem like this. So in this problem, you have a set of high temperatures and it's measured in Celsius. It has a mean of 20 and a standard deviation of 3. Then they put all the different values in this big formula of 9/5 C plus 32. What is the new mean and standard deviation? Well, for mean, remember the truth. We change mean either when something is added to it or subtracted, or even when something is multiplied or divided by it. So both of these would change the mean in some way. So if the mean of the original is 20, we would just take 20 and we can just go ahead and say 9 divided by 5 times 20 plus 32. You can just literally do that with a mean, and that's going to show you the new mean. So it would become 68. So the mean of this must be 68. This one cannot be the answer. For the standard deviation though, remember you only do the multiplication. The adding has no bearing on the standard deviation at all. So 9/5 C. 9/5 times 3 would be 5.4, which if you do the fraction on it is equal to 27 divided by 5. So therefore the correct answer for this would be B. And just think about this for a second. It does in fact make a lot of sense because of course the mean is probably going to get a lot bigger. Just, makes sense. Fahrenheit is like bigger than Celsius for most of the values that matter. Standard deviation as well, it's probably going to get bigger, but not this much bigger. It's not going to become literally 187 divided by 5. That's going to be a bit too crazy for my liking there. Now you understand that, let us go on and talk about some figures real quick. So the big thing with figures is that they're fairly simple. You just have to not make some very simple, small mistakes. The big figure you must know though, and the one that you're most likely to make a mistake on, is a frequency table. What this is exactly what it sounds like. It shows the frequency of different values in a data set. The big thing you must know is that these are the actual values, and this is the amount of times that each one shows up. So if I was to write this, I could say A is equal to 2 instances of 5. So 5 and 5. It would be 3 instances of 6. So 6 and 6 and 6. 1 instance of 7. So just 7 there. That is what's going on. There is no instance of 2, 3, or 1 in here because those are just the amount of times they show up. So if you ever see this, it probably is not going to have the labels on top. So you just have to know the right side is the amount of times it shows up. The left side is the different numbers themselves. Pretty good stuff there. I'm going to show some examples of this in a second. Okay, second thing here is a dot plot. This is much, much simpler. You can pretty easily just see what's going on here. If you can't see what's going on here, you might be kind of cooked because we have like these different numbers down here, 56, 60, 64, and these are the amount of times each one shows up. So this one shows up 2 times, this one shows up 2 times, 3 times, bunch of times, all that stuff. That is what is going on here. If you were to write it in here, it would show something here like 56, 56, I don't really want to write down the rest, but yeah, 2 of those. Same thing with a bar chart. This is just another way of showing a dot plot, just with bars instead of dots. So exact same thing. This is the amount of times each one shows up. That's what's going on here. Last one, it's a bit more confusing, is a histogram. This sometimes does show up. What is going on here is you're not just seeing the amount of each number, you're seeing a range for each one. So it's saying here that there are 2 different values that are between 20 and 30. So for those values, it could be something like 21 and 21. It could be something like 27 and 26. It could even be something all the way like 29.99999. The only thing it cannot be is 30 or anything below 20. So it cannot be exactly 30. 30 is reserved for this next bar over here. You just do all the ones before 30. Those are what would be included in that one there. So it could be 29.999. It could be 29 again. It just cannot be literally 30. Then it would not be counting for that. So that's what each of these are. It's just a range. So 30 to 40, 40 to 50, 50 to 60, that kind of stuff. And the last thing I just want to quickly go over here is what is known as a symmetric data set. What symmetric means is that there's one thing in the middle that has the most amount, and then all the other ones on either side look pretty much exactly the same with the amount of each. So there would be the same amount as 4 as there is of 6, same amount of 3 as there is of 7, and 2 and 8, same thing, and the same thing for 1 and 9. That is what a symmetric data set would be like. The big thing you need to know is when it is symmetric, when it is truly the case that they are the exact same on both sides, the mean is now the exact same as the median. Now, if you need some convincing on this, I could show you an example, but just really think about it. Like, mean value, in many respects, does show the central point of a set of data. I know I gave you that example with the crypto billionaire, but that's just because there was somebody on this side that was like way up here, like, unbelievably high on this side. When it is not the case that that's happening, it would literally just be the central point of the data. In a perfect world where everybody has like an equal amount of wealth, you have a mean that is actually reliable for the average wealth of that community. Some quick examples here. So this has a dot plot of the amount of rainfall in millimeters on 11 different days in a city. It says there's one thing here with a rainfall of X millimeters and it's added to the data set. If adding it, the mean becomes 5.25 and the median becomes 5, which could be X. Again, simplest way of solving this, I'm just going to go ahead and though it's a bit tedious, I'll just go ahead and write out what this data set would look like. So 5, 5, 5, 6 and 6, 7 and then 8. And I'm just going to leave in here an X1. That would be the last value we did not know yet. So add slider there. And it says after adding it, the mean becomes 5.25. So I can say the mean of A, we have to find where it's going to become 5.25. So I can just go ahead and honestly just move it around. And yeah, are we going to get 5.25 anywhere? Yep. If X is equal to 8, it becomes 5.25. That works. It says that the median must become 5. So we can just try that as well. Median. Yep, it would also be 5, so therefore 8 works for sure. Frequency table. So we have values here in the frequency. It says how much greater is the mean of the data set than the median. So I could go ahead in here and just plug in a random number for A. So I could say A is equal to 1. So there's one instance of 1, 2 instances of 2, 3 of 3, 2 of 4, 1 of 5. And that would work. We could try it out here, get a great answer. But remember, we're trying to solve these the easiest way possible. And sometimes the easier way will be even easier than that. Because think about it, this would be a symmetric data set. We have a bigger value here, smaller here, and then the same over on this side as well. So remember the rule that I just laid out for you. The mean must be equal to the median. Therefore, the answer to this one would just be 0. They must be the exact same number, so it would not be any bigger at all than the other one. Dot plot time again. So this shows the amount of volunteer hours completed last month by each of 11 different students. One student's volunteer hours was recorded as 2, but the correct value should have been 10. After correcting the data, which choice describes how the mean and all this different stuff changes. Okay, so just start off here. I actually had put some stuff here before. So yeah, we had this value of 2 here, and this would go down here to 10 instead of 2. How is that going to change stuff? Would the mean increase or decrease? Well, that's kind of obvious. Kind of for the crypto billionaire example, we're taking a smaller value and making it very big. With our people up here, if we gave this guy like $1 billion and didn't change anything else, the mean is obviously going to get bigger. There's going to be one person who's much richer than everybody else now, so the whole thing is going to get much higher than it would be before. Just obvious. Hopefully it just makes sense logically to you. So therefore, it makes sense for the mean to increase, not to decrease, so therefore this cannot be it. What about the median? Would that increase or decrease? Well, this one we can actually just go ahead and look at for a second. So for the first example, what would be the median of this data set? Well, we have to see what would be the middle value. So 1, 2, 3, 4, it says there's 11, so 4, 5. So the median value would be 6 here because there's 5 on this side of that, 5 on this side. What would it be after we move this value over here? Well, 1, 2, 3, 4, 5. Again, it would be 6. So the median also would not change at all. Median cannot increase. What about the range? Okay, pretty easy stuff here. For the first one, we had this thing here, 9 minus 2 would be the range, so that would be 7. For the second time, though, we have 10 minus 4, so that would end up being 6. So the range must decrease at least a little bit, so therefore the answer would be B. One more example here, we have histograms now. How are we going to solve a histogram problem? So it says there are two sets of data of 24 integers each. And it says for each histogram, each interval represents the frequency greater than or equal to the left endpoint. Okay, it just says what a histogram basically is. For example, it gives an example here, probably too much information in this problem, that's fine. Let x be the mean of dataset x, and let y be the mean of dataset y. Which choice is the smallest possible value of x minus y? Okay, so what can we do here? In order to make it the smallest possible value we need to make sure that x is really, really small and y is really, really big. Think about this for a second. If x is literally something like 2 and y is 1, that's going to have a much smaller thing than if x was equal to 5. So we want x to be as small as possible and y to be as big as possible. How could that be the case? Well, remember, this is a range for each one. It's not saying that it literally is equal to one of these values. It's just a range for all the different things it could be equal to. So let's just go ahead and cook the books for a second. Let's just pretend like they must be the smallest value possible for x and the biggest possible value for y. It says here that they're integers, so we don't have to worry at all about that thing before, like 29.999. It can just be 29 as the biggest possible one. So we can just go ahead and do this. For x, we can say that it would be 2 instances of 10, there would be 5 of 20, there would be, 9 of 30. Okay, this is going to be a lot, but I guess it's going to be worth it. There would be 8 instances of 40, and that would give us x. Okay, for y now, just exact same thing, except now we're trying to go for the biggest one we can. So there would be 4 instances of 29. There would be 6 instances of 39. There would be 10 of 49. And then finally, there would be 4 of 59. Okay, so if we do the mean of x, that would be that. And if we do the mean of y, that would be that. Then if we go ahead and just take this number and then minus this number, it is going to end up being negative, but it would be negative 15.25. If we look at these, which one works for that? Well, if we break this into fractions, it could be 61 over 4, so therefore A must be the right answer over here. Good stuff there. Interesting histogram problems, sometimes stuff like that can show up. If your SAT score is currently below a 1400 and you're trying as hard as you possibly can to get to a 1400 or higher before your next test, check out Mission 1400 Plus with the link in the description below. This is a full community geared around helping people lower than 1400, break past the 1400 barrier, and finally get to 1500 and beyond. Every person in here gets my full math course and full reading and writing course and a full roadmap going through everything so they know exactly what they need to do to improve their score, plus also 28,000 practice questions and realistic practice tests as well. I really recommend it. We've had a ton of people improve their scores already through this, so I definitely think you could as well if you join. Plus, we have a free trial, so there's literally no risk at all if you want to join just to try it out. That's all for me today. Hope you do well on the next SAT and make sure to always stay Gucci.